Assalamualaikum and salam sejahtera. In this video, we are going to be discussing the questions on assignment 6. Question 1 and 2 is based on the transfer function given here. Question 1, you need to identify the gain, and question 2, you need to identify the phase. Okay, the first step is to replace all the assets with j omega. Then we have to convert this transfer function into the standard form by dividing out the poles and 0. So the standard form is always in the form of 1 plus j omega or 1 plus j omega over n, something like that. If we look at the numerator, which is 0.6 times j omega plus 1, this is already in the standard form. This also tells us that we have two positive terms in our gain equations. If we look at the denominator, we can see that we have poles at the origin and we also have j omega plus 10. This is not in the standard form, so we have to divide out the poles to convert it to a standard form. And we have this. And based on the denominator as well, we know that we have two negative terms in our gain equation. Okay, so again, we have a constant, we have simple 0 with a gain of 20, and we also have a pole at 0 with a gain 40 because of the squared. We also have simple pole with gain 20. So the overall gain equation for this transfer function is as shown here. So the first two are from the constant and the 0, and they are positive, and the next two are from the poles and they are negative. The constant gain will have 0 phase. The simple 0 will have inverse tangent of omega. The pole at origin squared will have 2 times 90 degrees and is negative because it's a pole. And finally, the simple pole will have an inverse tangent of omega over 10 and is also negative because it is a pole. Just like the gain, all the zeros will be positive and the pole will be negative. Now for question 3, shown in this figure here is the both magnitude plot, and you are required to identify the transfer function for this both plot. Okay, first let me redraw the graph and put the frequency axis at the origin. Okay, now we can clearly see the graph. From here we can see that there is a shift in the graph and it doesn't sit at the 0 dB line. Okay, so it shifted upward to the 20 dB line. So in order to solve for the gain, we equate the 20 dB equals to 20 log gain and solve for the gain to be 10. Okay, now we go back to the figure given to you in the question and we look at the first 20 dB per decade slope. And we can see that this line crosses the 1 radian per second, which means that we have a 0 at origin. So this slope plus 20 dB per decade at origin will give us the j omega term. Okay, now we look at the straight line here. One rule that come in handy in deriving transfer function from both plot are, when you see at the corner frequency, if the slope increases by plus 20 dB per decade, you know that there are zeros present in the transfer function. And if the slope decreases by minus 20 dB per decade, you know that there are poles present in the transfer function. Okay, now corner frequency is just a point where the slope changes. In this case, we have a corner frequency at 1 radian per second and 10 radian per second because that is the point where the slope changes. Okay, back to this straight line. So at this corner frequency 1 radian per second, we can see that the slope changes from plus 20 dB per decade, right? From plus 20 dB per decade to 0 dB per decade. So this means that the slope decreases by minus 20 dB per decade. Here we know that there are poles present in the transfer function. So at a pole of slope minus 20 dB per decade, remember that it goes from plus 20 dB per decade to 0 dB per decade. So there is a decrease in slope by negative 20 dB per decade. At this point, we have a pole and it gives us the expression of 1 over 1 plus j omega. Okay, next we look at the corner frequency of 10 radian per second. We can see at this corner frequency, the slope goes from 0 dB per decade to negative 40 dB per decade. So there is a decrease in slope by minus 40 dB per decade. We know that because the slope decreases, there are poles present. And because it is minus 40 dB per decade, we have the squared term in the transfer function expression. So the overall transfer function for this boat plot is as shown here. For question 4, you are given a series RLC network with R equals to 4, L equals to 80 millihenry, and C equals to 1 microfarad, and you have to calculate the impedance at resonance. So at resonance, the capacitive and inductive behavior of the circuit are equal in magnitude, so they cancel each other out, and the circuit becomes fully resistive. Therefore, the impedance at resonance is just 4 kilo ohms. Okay, for question 5 is based on the figure given here. You need to calculate the resonant frequency omega naught, the quality factor Q, and the bandwidth B for this circuit. Okay, first and foremost, we need to transform the circuit so that it becomes purely parallel circuit. So we know how to do this. We just use source transformation. Okay, now that we have this, we can combine the two resistors in parallel, and now we have a parallel RLC circuit. Okay, from here you just apply the equation to find the omega naught, the B and Q for the parallel RLC circuit. You can refer to this table right here, which is, if I'm not mistaken, is table 14.4 in your textbook. And you will find the value for your omega naught to be 5000 kiloradian per second, your bandwidth to be 84.722 radian per second, and your quality factor is 59.016. Okay, for question 6, you also have parallel resonance circuit, but now you are given the half power frequencies and you are supposed to calculate the quality factor and the resonant frequency. So let's just recall the half power frequencies equation here. So for this one, you can actually use either omega 1 or omega 2 to solve for the omega naught resonant frequency. In this case, I used the omega 1 to find the resonant frequency, and I found the value to be 5.0 megaradian per second. Don't forget to convert your 40 kiloradian per second into megaradian per second before you try to solve the problem. Okay, and next you are supposed to find the quality factor. You can just refer to the table from the previous slide, and you will find that your Q is equals to 125. For question 7, we are dealing with filters, specifically band pass filter. So you are given a series RLC band pass filter, and you need to find the range of frequency that will be passed by this filter. So basically what you need to calculate is the lower cut-off frequency and the upper cut-off frequency to find the range in which the band pass filter allow the frequency to pass. Okay, after that, you also need to calculate the quality factor for this circuit. So what you can use to find this upper and lower cutoff frequency is use your two half power equation. And in order for you to apply this equation, you need to find the resonant frequency as well as the bandwidth. So similar to the previous problem, you just go to the table of series RLC and solve for these two parameters, and then apply it to find the two half power frequencies. Now that you have these two half power frequencies, you need to convert the kiloradian per second into the frequency in hertz. So you just divide the value of your resonant frequency by 2 pi, and you will find the value of the frequencies. And therefore, the range of frequencies that will pass by this band pass filter is between 1.55 kHz to 1.65 kHz. And for the quality factor, you just Use the value of your omega naught and bandwidth to find the value of Q, which is equals to 17.86. So that's it for assignment 6. You have 7 questions, and as usual, I will distribute 2 to 3 questions, very easy one for you to answer as part of your attendance and participation in this week's tutorial. Thank you very much.